outline of my presentation is as follows. I would like to first give the reasons for assessing the combined transport processes involving carbon dioxide and chlorides. I would like to then present the objectives of the investigation, give some description of the experimental work, and then give the data obtained in the form of carbonation profile and chloride profile, and use them to conclude the outcome of this research. So the first one is the reasons for assessing the combined transport. And this is very much construction related or infrastructure related talk. So I am showing here 3 bridge structures. We can actually apply the same for buildings exposed to different environments as well. So the first one is the Hanjubei Bridge in China. The second one is the Brixby Creek Bridge in California. Third one is a highway tunnel and a bridge in north of Italy. In all these cases, if you look at the exposure, you will see that there is the exposure to carbon dioxide, there is the exposure to chlorides, there is the exposure to sulfate, there is the exposure to moisture. And in some cases, there is the combination of freezing and thawing as well. So when we deal with the performance of these structures in different exposure conditions, we need to look at the combinations of the exposure environments. So in this particular talk, I'm going to actually use the carbon dioxide and chlorides. That doesn't mean that only those two will have to be applied in all these cases. There will be, for example, sulfate in some cases, and the moisture presence is always there. So the objectives of the investigation, primarily to study the deterioration mechanisms of typical concretes under the combined CO2 and chloride environments. And also using the data to propose a protocol for the development of durability assessment using non-destructive tests or embedded sensors. There are different models available for predicting service life, and I just wanted to use the data from this particular strand of the work to highlight what are the existing limitations, what changes are needed to existing models. So an outline of the experimental program. We have here the carbonation and chloride ingress in concrete under independent and combined exposures to CO2 and chloride solution. So first we look at the independent exposure to these and then the combined exposures. We'll be looking at the microstructure. We'll be measuring permeation properties. We'll be looking at the progress of carbonation and chloride ingress, and also the variation of the electrical characteristics of the concrete. And using all of them, the capability of NDT methods for assessing the degree of carbonation and chloride ingress in concrete under the combined exposure regimes will be arrived at. And in order to study this, we considered 2 sets of concretes. One set is, as you can see, with values less than 0.4 here, and the other one is actually with value 0.55. And they refer to the water binder ratio. That's the amount of water added in the concrete for manufacturing them. So in some concrete mixes, the water content was low. In some other mixes, the water content was high. And these mixes contained Portland cement alone and combinations of other cementitious materials like a pulverized fuel ash along with microsilica or silica fume. And these combinations were tested, as I said, at 2 different water bind ratio combinations. And the effect of that is, as you can see, the strength of the concrete is different. The higher water bind ratio gave lower compressive strength, and the lower water bind ratios gave the higher compressive strength. So in practice, we use concretes of different compressive strengths for different applications. And therefore, we were looking at two ranges to see the effect of this combined regime in those two combinations. And in order to do that, we simulated the exposure environments in the lab. And to do that, we looked at the BSEN 206, which is the European standard. And this is the exposure to carbon dioxide, where you have a relatively low humidity. And this one is the one where you have the exposure to wetting and drying. And particularly this particular exposure regime is almost like a submerged condition in presence of chloride. And the next one is seawater exposure, again completely submerged. These exposure classes were simulated in the lab for the investigation. And we assumed a design service life of 50 years for the concrete. And the minimum compressive strength was 30 megapascal, as you can see, that was achieved. And the expected workability, ability to work with the concrete, measured in terms of one parameter called slump, was 50 to 90 millimeter. And you can see that that target slump was also achieved for both concretes. Okay. Now, what properties were measured in this study? We measured, obviously, various transport characteristics using two test techniques called air permeability and chloride migration test. The electrical resistivity was measured using embedded electrodes. I will show that in a minute. And then chloride profile and carbonation profile were obtained. And then the relative humidity profile also was obtained. And all the details of the test techniques are available in a publication in Construction and Building Materials Journal. You can actually get further information there. So this is the exposure regimes used. For the accelerated carbonation test using carbonation chamber, we had a carbon dioxide concentration of 5%, and the temperature and the relative humidity were 20 and 65 respectively. In the case of chloride immersion, the chloride solution was prepared with this kind of concentration, 165 grams per liter, and the air temperature was 20 degrees and solution temperature also was 20 degrees. So this is to control all of the experimental investigations during our study. And this slide shows some of the test techniques themselves. And for example, to get the chloride content, we use this equipment called a profile grinder. This is capable of grinding the concrete to 0.25 millimeter depth and then get the dust sample, which can then be analyzed using the auto titrator shown here for the chloride calculations, or chloride determination. And the dust sample can be used for finding out what is the pH of the dust as well by digesting the dust in deionized water. And that also can be used for assessing what is the consumed hydroxyl ions due to the degree of carbonation. And then to measure the relative humidity and electrical resistivity, this is the setup used. You can see holes of depth 10 millimeter, 20 millimeter, 30 millimeter, and 40 millimeter. And in addition to that, the surface measurement also was used. That means we were able to measure the relative humidity at depths of 0, 10, 20, 30, and 40 millimeter in the prefabricated holes in concrete. And the resistivity was measured by embedding electrodes in the concrete at different depths, as you can see here, and then measuring the resistance across pairs of electrodes in the concrete. And the exposure regime, it's quite a complex regime. So initially the concrete was cured for 56 days, 1 week in water, and then wrapped in polythene sheet, and then kept it at 20 degrees Celsius. and that is kept there for the remainder of the 56 days. And after the concrete has completely cured, we had two sets of exposure conditions you can see here. One is where we conditioned the samples for relative humidity, and that is done by drying and redistributing the moisture. So we were expecting to get 65% relative humidity in the concrete, and then it was exposed to 5% CO2 and 20 degrees Celsius. This Y stands for different durations of exposure, and the durations were 1, 2, and 3 months. After that, samples were also exposed to chlorides. So for chloride exposure, we saturated the concrete sample first with incremental immersion, and then immersed in this sodium chloride solution at 20 degrees Celsius, again for 1, 2, and 3 months. So that is the chloride exposure following carbonation. And in the second regime, we had carbonation following the chloride exposure. In reality, you get to combinations of this. You have chloride exposure followed by carbonation, carbonation followed by chloride exposure. So we were trying to simulate these combinations in the laboratory. So let me show you the carbonation profiles. And this actually shows the two water bind ratios for Portland cement concrete for 3 durations of carbon dioxide exposure. This one is actually, again, 3 durations of carbon dioxide exposure after subjecting to 3 months of chloride exposure. And here it is different durations of chloride exposure first, followed by different durations of carbon dioxide exposure. Clearly, you're seeing a difference in the consumed calcium hydroxide content with depth. This is the surface and up to 30 millimeter depth. If you compare these three, very clearly, you're seeing 3 different profiles of hydroxyl consumption within the concrete. So if we assume this as the way concrete is going to carbonate and model that for predicting the service life of this concrete or concrete structure, it cannot be right because you're seeing further changes to the consumption of the hydroxyl here. And that depends on the amount of chloride present. And in here, with the good quality concrete, this effect we see here is not as dominant. So for this concrete, assuming that there is only one particular regime and a model that should be sufficient, but for this concrete, that modeling is not sufficient. Now, if you go to the next type of concrete, that's the pulverized fuel ash concrete mix. Compared to this here, you just to see the way this concrete behaved. The surface conversion is different and the penetration into the concrete is different. That means the degree of carbonation right from the surface into the concrete is different. And again, we are seeing the effect of chloride present before carbonation in the consumption of the hydroxyl ions. So the inference is we cannot just simply use a model for one type of concrete for predicting the service life of another concrete. It has to be by taking account of the material, the cementitious material used in the concrete. And again, if you look at here, there is not much of a difference. That means the model which we use here possibly should be sufficient for predicting here as well. So in good quality concrete, high performance concrete, this combination effect is minimum. However, in most of the concretes we use in structures, there is a need to consider the combinations of the exposure as well as the type of cementitious material. And again, if you have another type of cementitious material, for example, PFA plus microsilica, you see that the deep penetration has changed. And again, you have actually changes internally as well. However, in this case, there is a bit of a change between the first one and the second and third due to the presence of microsilica. So possibly to a lesser extent, we have an effect here, but the major effect is for the normal types of concrete we use in constructions. Now, let me actually present the chloride profiles. So to do that, first thing is, because we are going to condition the sample after the chloride exposure, before the carbonation exposure, we want to know whether there is any effect due to this conditioning. And here we are seeing that there is no effect due to conditioning, which means that the test conditions can be used for studying this effect. Now, we have here the chloride concentrations with depth. Of course, you can see with the different durations of chloride exposure, the surface chloride content is different. Interior to the concrete, possibly not much of a difference you see for the first concrete. In here, on the other hand, the presence of carbonation or the exposure to carbon dioxide is causing redistribution of the chlorides. The surface concentration, the maximum concentration of the surface observed here has changed, and here you can see this pushing inward. And when you go to another exposure combination, the chloride content maximum has been shifted again interior to the concrete. So if we predict the corrosion caused by chlorides using this model, that cannot be applied to these two combinations. Now, here we are seeing really unusual pattern. The surface chloride is actually very high compared to this one. So the model predicted using very high surface chloride is going to give a totally different service life for this concrete compared to that concrete. So what I'm saying is simple application of predictive models should not be used for estimating our service life. The effect of combinations should be used. And that is again seen for the other type of concrete in the PFA. Now you see that the big surface chloride concentration we found in PC concrete is not seen in the PFA, whereas when you go for the combination of microsilica and PFA, again the surface chloride is going up. So overall, we thought, okay, let's actually see the relationship between chloride profile and consumed hydroxyl distribution. So the first set of graph is the chloride, the second set is the hydroxyl ions. Interestingly, what we are seeing is the peak chloride content is coinciding with a particular value of the consumption of hydroxyl ions, which means that the degree of carbonation influences this peak value of the chloride content. So that relationship then needs to be brought into service life models. That is actually our main conclusion. And that's what I have stated here. Okay. So now moving on to the conclusions, chloride exposure followed by carbonation, both the peak value and the extent that the depth of penetration of chlorides of the redistribution are related to the degree of carbonation and the type of binder. Carbonated concretes exposed to chlorides increase the penetration of chlorides much deeper into the concrete. So that means carbonation is actually causing more penetration into the concrete. And then combine the carbonation and chloride exposure regime, there is a complex interaction between carbonation profile and chlorides. We need to actually take that into account in service life models. So just wanted to actually, based on that, give some recommendation, which is that we depend very heavily on cubes and cylinders for assessing the quality of concrete in structure. That has a huge limitation. What is ideally needed is controlling the specification and design based on service conditions and requirements of performance, and using numerical simulation for assessing the performance and the decay of that performance, and then specify the concrete mixes and the raw materials to take account of that. And then the real-time performance of the material should be monitored and adjusted. And then during the service life, we need to use non-destructive tests and sensing techniques to get feedback of the performance and then predict the service life of structures. So it is not a simple question of linearly considering the service life. It's a complex phenomenon, and that complexity needs to be considered in service life models. Either they use in the fresh concrete or for hardened concrete, there is the need to adjust those. So with that recommendations, I conclude and finish. Thank you for listening.